Okay. So we want the force on QB due to Q and QA. Okay. Well, we can completely write out the force exerted by Q on QB. I guess I could call this, if I could write QA and QB. Force on QB would be just the same expression we have here. The force exerted by QB on Q is going to equal an opposite of that. They exert equal and opposite forces. Now you could write it out in terms of Coulomb's law, and your vector would just be negative B1I minus B2J, right? From B1 to 0, you go negative B1. Going from B2 to 0, you go negative B2. Okay? So we'll call this the force exerted by the particle at point B to the particle at the origin. Then the force exerted by the particle at B on the particle at A. Force here would be when I wrote this down, I did KQA. I should have written it as KQ times QA, as I did here. And I used a capital QA here. I probably should have used a lowercase QA here because I used a lowercase q here. And this one should have been lowercase. So I apologize for that. Now let's get it right. And it's just simple. Again, it's K times the product of the two charges involved. The two charges here, the charge of B and the charge at the origin, QB and Q, divided by the square of the distance, which is the square root of B1 squared plus B2 squared, but it's not the square root, it's the distance. And then it's times negative B1I minus B2J over square root of B1 squared plus B2 squared. And I don't remember if I commented over here, I was tempted to. This and this go together to give us a 5/2 power, right? Of B1 squared plus B2 squared. 3/2 power, sorry. Okay, then it's KQBQA. You want a vector from B to A. You want your vector from B to A? I'm going to write the vector from B to A here. The I component is going to be B2 minus B1. And it's not B2, it's A1 minus B1. Okay. A1 minus B1 and A2 minus B2 J. That's the vector from here to here. It's A1 minus B1 in the I direction and A2 minus B2 in the J direction. And then that's going to be over the square root of sum of the squares of these components. And your denominator here is just you just write it down. So you want to be sure you can do that. You know how to do that. Okay, that's all I want to do with this picture right now, but you know, I'm going to give you some, especially after break, we're going to get into harder problems of building these things, okay? Right now, we're just working at the level of the transition problems. So we want to be sure we have all this stuff down, and I think you're going to see how this works when you really master these transition problems. I did give you a link to a set of transition problems without solutions. And you should be able to go down through those problems and solve them without looking at anything. Okay? Probably won't be able to do that in your first try, but there are several sets. So you should be able to, at least, I would start by reading through those problems and just making notes. Okay, I would use this, I'd use this, I'd use this. You don't even have to necessarily associate it with one of the problems. Just see how much of the stuff you've got written in your notes from those problems, from the problems with solutions. And see how much of that you've got every time you go through those problems. And you can go through them pretty quickly. You're going to know more until you start seeing the whole picture. Okay. Or at least until you got a good grasp of the building blocks. Now, something different here. Now, okay, I've got a charge Q here. I'll use a capital Q. All right. And you got a sphere. Bad looking sphere though. You got a sphere of radius A. Okay. At the surface of the sphere, you have a uniform electric field. It's always perpendicular to the surface. E's constant, since it's a sphere, your E is going to be in the direction of your radial line. The radial line is always tangent to a circle or a sphere. Area of the sphere is 4 pi A squared, which you should always be able to derive by integration. Okay? Which is simpler than the construction the Pythagoreans use, but you do that too. Area of the sphere is 4 pi A squared. Product of E perpendicular. And of course, E always is perpendicular, but I'm going to write E perpendicular anyhow. Not because it's always perpendicular, because if I move this charge over here, it's not always going to be perpendicular, right? And I've got a question here, either that or you're having some kind of spasm. I don't think so. You look too stable for that. So let's see. The question was, that is a surface area, right? Yes. It's the only area we can talk about on a sphere. Unless you go into higher dimensions and do all kinds of stuff that I don't know how to do. Okay. Area of the sphere is 4 pi A squared. You should recognize that is the formula for the surface area. And the word surface is good. I didn't bother to write it down because it's implicit. Okay. Product of E perpendicular and A is just four pi A squared E perpendicular. Okay. That's the electrostatic field, electrostatic flux of the field through the enclosing surface. That terminology is important. It's a surface that encloses charge Q. Okay? Make sense? It's a flux. It's like, that's how much field is penetrating the surface of the sphere, right? You just multiply how much the field is and multiply it by the surface area. I have a lot more I could say about that, but let's hope that suffices to give you the first general idea of flux. Now, in this case, I could ask you to draw it, but we're not going to take last time, but what's the field going to look like? It's always going to be going straight away from the charge, right? So the field lines are going to be like this. They should be more equally spaced, but they are equal angles, but they're close enough. Okay, so the closest point on the sphere is here. We have a pretty big electric field here, right? Compared to the others. Now this point is 1, 2, 3, about 4 times this point down here. It's about 4 times further from the charge. So that the field down here is going to be 1/16 as great. So it's going to be a tiny field. Now, over here, we're going to have a field that's maybe 1/4 as great as the one I drew there. And at this point, maybe similar. Okay. At this point, it's going to be a little bigger. But it's in this direction, and this is even bigger, and this is even bigger. Okay. Now, I'm not drawing these with any great accuracy, but you're getting the idea. Something's messed up here. That should be a little longer, that should be a little shorter, whatever. That's not particularly accurate. The relative sizes aren't quite right, but you get the idea that the field isn't constant. And the direction is almost never perpendicular to the surface. Maybe here, and maybe somewhere about here. Okay, the direction is almost never perpendicular to the surface. Okay. Capital Phi sub E for the flux of the electric field. We'll talk about magnetism. I'll be using phi sub B. when I'm talking about electrostatic potential, I'll use a lowercase phi with no subscript. Okay? And maybe I'll change notation on you, but for right now, we'll stay with that. Okay, now, my point is, still, I sub B equals the same as it does over here. It doesn't matter where you move this charge inside this enclosing sphere. Total flux is going to remain the same. That's just Gauss's law, which one of you should recognize from multivariable calculus toward the end of the course. And the rest of you, all of you, all the rest, will have something to live for. You live to the end of the semester so you can see Gauss's law. Okay? If you have nothing else to live for, and you probably do because you okay. Seriously, it's really pretty neat. It's a pretty neat result. It doesn't even have to be a sphere. For any surface enclosing a charge or collection of charges or charge distribution, when I say enclosing, it has to be a closed surface because only a closed surface can enclose anything. Okay? So I don't have to say it's a closed surface. That's implicit from the fact that it encloses. Now, there could be some topological qualifications in some of this, but we're not going to worry about that. Make sure I'm on screen. Well, I left off some terribly dumb. No, never mind. Pi E equals 4 pi k cubed enclosed. Now, where does the 4 pi k come from? What's E perpendicular here? It's KQ over R squared, right? Well, R would be A, so it'd be KQ over A squared. So if E perpendicular is KQ over A squared, this becomes 4 pi KQ. Make sense? You're going to see it in your introductory problem sets or your transition sets, okay? So this is identical to this. If we just write out what E perpendicular happens to be in this specific case. We can't write it out here because it's different everywhere, okay, on the surface. But here it's the same everywhere on the surface, and that's the big deal, okay? Well, what good is that? Okay, well, I'm going to give you an example. Say that we have a bunch of card Charge density lambda, where lambda is charge per unit length. Now, this is impossible, but we can still hypothesize it on the entire x-axis. That would take infinite charge, right? If we have a non-zero charge density on an infinite line, we've got to have infinite charge, and the universe doesn't have infinite charge, so we can't actually do it. But it's still a very useful approximation, and I'll go into detail on why. I want to know what the electric field is at this point. Well, let's say this point. The electric field at distance A from the axis. You know what I do? Okay. I was going to use that graduated cylinder, but it's got ends on it, so I can't do what I'd really like to, which is this. Had to go all the way to the opposite corner of the lab, but fortunately I'm in good shape. I can make it. Okay. Let's just say that this is a section of my axis. I take a cylinder of radius A, and I surround the axis with that cylinder. Okay, my hands are kind of in the way. You can see what's in a single cylinder is on the axis, or the axis of the cylinder is the axis containing the charge. So that's what we do. I'll just depict that. There's the cylinder, right? By symmetry, every point of the cylinder is at distance A. We're just talking about the sides of the cylinder now, not the ends. Every point of the sides of the cylinder is at distance A. And the field has to be radial. Here's the end view. Here's our cylinder. Field lines have to be radial, because if they weren't radial, I could do one of two things. I could rotate the cylinder a little bit, and anything that isn't radial is going to be in a different place. So it's not going to look the same. It's going to violate symmetry. If everything violates symmetry in the same way, let's say everything is at an angle of 10 degrees with the rate to the counterclockwise from the radial line all the way around, okay? Then, now it's kind of difficult to invert an infinite axis, but say if we just imagine inverting it and looking at it from the same point, all those deviations are going to be in the counterclockwise direction. So because of symmetry, then I say that E is constant and radial. Okay, now I haven't addressed every possibility. Obviously, if it's not constant, then again, rotating it will change the picture. So a rotation would still be detected. If it's not radial, then flipping the ends will make it not radial in the opposite direction. Okay? You know, if it's this way, Then I flip this thing, it goes, and it's, well, I didn't do that right, but it's this way, okay? The field was coming out like this piece of chalk here, if you can see it. And I turn it here, now the piece of chalk is pointing that way instead of that way. So by all those symmetries, now it was trying to get away from me. It was trying to fall on the floor. I couldn't see it, but I knew it was going to come out. Okay. By symmetry, E is constant and radial. And I tried to keep it slow so there wouldn't be any sonic booms. I got to control my reflexes when I'm around ordinary mortals. Okay. By symmetry, E is constant and radial. No flux through the ends of this thing because the field is parallel to the ends. It can't penetrate the end if it's parallel to them. Okay. So phi E equals, first of all, lambda L. Well, let's just say charge enclosed. Q enclosed is lambda L, where L is the length of that cylinder. There. 4 pi K, Q enclosed. Which is 4 pi K lambda L. Also, pi A equals 2 pi A L. Now, why is that? The surface of the cylinder, if I cut the cylinder and spread it out, it gives me a rectangle that's got dimensions L by 2 pi A. Circumference, I slit this thing, spread it out, the circumference becomes one dimension of a rectangle, L is the other dimension. The circumference is 2 pi A. 2 pi A L, very simple, something you should have learned in grade school, well, middle school, okay? But it don't get to teach much in middle school these days. 2 pi A L times E, since E is always radial. It's always perpendicular to the surface, okay? Well, that means this equals this, and we can solve for E. Take this equal to this and solve for E. It's 2K lambda over A. If I solved it correctly, I mean, 4 pi divided by 2 pi is 2. L divided by L is 1, and you got lambda over A. So that's it. That's your electric field. Argument halfway makes sense? Well, you're going to see it, and it's important. I'm going to use that. Introduce the idea of a capacitor. Okay, so let's say we have this little cylinder. Now it's actually a cup. It's got an end, so you cut the end off and you got a little cylindrical surface, right? And then take another one, just a little bigger, and put it around this one. Maybe make them longer. And you have a cylinder inside a cylinder, and they're coaxial. They have the same axis. So it's something like this. Cylinder inside a cylinder. We take a battery or something, okay? And we pull charge off of one of these cylinders and put it on the other. That would leave us negative Q on the inner cylinder and Q on the outer cylinder. Now the surface, the circuits we've looked at, it basically just circuits that we make up with batteries and nichrome wire, resistance wire. We said that there's no place for charge to accumulate. But here you have a place where you can separate some charge. Okay, you separate some charge from the inside, and you take some charge off the inside and put it in the outside. Now you've separated charge, so you've actually stored some charge. Okay, now if we use cylinders of this dimension and metal cylinders, they'll do that, but they won't store much charge. Okay, and we can store a lot of charge. We might be able to do that. Let me pause for a second.